Welcome to TechLab, where we break down complex robotics concepts into clear, structured understanding. Let me ask you something. Why doesn't a drone fall out of the sky when the wind hits it? How does a self-driving car know where it is even when GPS signal drops? And how does a robot keep track of its position while moving through a completely unknown environment? The answer to all of these questions is the same: sensor fusion. Today, I am going to break this down in a way that makes sense, whether you are just getting started in robotics or you are moving into intermediate level concepts. Let's start simple. Sensor fusion is the process of combining data from multiple sensors to get a better estimate of a robot's state than any one sensor could provide alone. But here is the important part. Every sensor makes mistakes. GPS drifts, IMUs accumulate errors, cameras were in low light, LiDAR can be affected by weather. If a robot trusted only one of these, it would fail. Sensor fusion is how robots reduce uncertainty. It's how they turn noisy data into reliable decisions. When we talk about merger, what are we trying to figure out? Robots typically estimate position and orientation, a map of the environment, object positions for tracking, and contact forces during manipulation. All of these require combining different sensor sources. For example, a ground robot might use wheel encoders for distance traveled, an IMU for orientation, a camera or LiDAR for mapping. Individually, each gives partial information. Together, they give stability. Now let's talk about the three levels of sensor fusion. In robotics, sensor fusion doesn't always happen in the same place. The key difference between the levels is simple. Where does the data get combined? There are three main levels: low-level, mid-level, and high-level fusion. First, low-level fusion, also called raw data fusion. This is where we combine raw sensor measurements directly before any processing. For example, imagine merging multiple IMU signals before doing any filtering or interpretation. You are working with the pure measurement. The advantage is that you keep maximum information and you can achieve the highest potential accuracy. But the downside is computational cost. It requires high bandwidth, precise synchronization, and significant processing power. This type of fusion is common in tightly coupled systems like IMU and GPS navigation. Next, we have mid-level fusion or feature-level fusion. Here, each sensor processes its raw data first and extracts meaningful features. For example, a camera extracts visual features. A LiDAR extracts geometric features from its point cloud. Then those features are combined in a shared representation of the environment. This approach is more efficient than raw data fusion. It's widely used in SLAM and perception systems. It offers a good balance between accuracy and computational cost. Finally, there is high-level fusion, also called decision-level fusion. At this level, each sensor runs its own independent pipeline and produces a decision. For example, a camera detects an obstacle, a radar system also detects an obstacle. Instead of combining raw data or features, the system fuses the decision. This approach is modular, scalable, and easier to engineer. However, it's slightly less optimal because some information has already been compressed before fusion. So to summarize, low-level fusion gives you maximum accuracy but high computational cost. Mid-level fusion offers balance and is common in real systems, and high-level fusion is modular and practical but slightly less precise. Choosing the right level isn't about which one is best. It's about what your robotic system actually needs. Now let's talk about the core idea behind the math. Don't worry, we are going to keep this simple. Most sensor fusion systems are built on something called probabilistic state estimation. That term might sound complicated, but the idea is actually very straightforward. Instead of asking which sensor is correct, we ask a better question. What is the most likely true state of the robot given all these noisy measurements. Because here is the truth. Sensors are never perfect. They all contain noise, they all contain uncertainty. So rather than choosing one sensor over another, robots combine them in a mathematically intelligent way. And they do this using a continuous loop called predict and correct. Step 1. Predict. The robot uses physics and motion models to estimate where it should be next. If it was moving forward a moment ago, it predicts it will continue moving forward. Step 2 is measuring. Now the sensors provide new data. GPS reports a position and the IMU reports motion, or camera sees features. Step 3 is correction. The system compares its prediction with the measurements. If they disagree, it adjusts the estimate, but not blindly. It weights them based on uncertainty. If the sensor is noisy, it trusts it less. If the prediction is uncertain, it trusts the measurements more. Then the cycle repeats. Predict, measure, correct. Hundreds, sometimes thousands of times per second. And that continuous loop is the heart of the sensor fusion. It's how robots turn noisy signals into stable, intelligent behavior. Now let's talk about one of the most important algorithms in sensor fusion, the Kalman filter. If you study robotics, estimation, or autonomous systems, this is one algorithm you absolutely must understand. The Kalman filter is designed for linear systems with Gaussian noise. In simple terms, that means the system behaves in a mostly linear way. The noise follows a normal distribution. When those assumptions hold, the Kalman filter gives an optimal estimate. Here is how it works. And notice how it follows the same predict and correct idea we discussed earlier. First, predict. The filter uses a motion model to estimate the next state of the system. Where should the robot be based on its previous motion? Second, update. It compares that prediction with the new sensor measurement. In the next state, it calculates the Kalman gain. This is the key step. The Kalman gain determines how much we trust the prediction versus how much we trust the measurement. If the sensor is very noisy, the filter leans more on the prediction. If the prediction is uncertain, it leans more on the measurement. And this process repeats continuously. Because of its efficiency and optimality under linear conditions, the Kalman filter is widely used in GPS and IMU fusion, linear tracking problems, basic navigation systems. In fact, many modern sensor fusion algorithms are extensions of the Kalman filter. So if you understand this one, you understand the backbone of the robotic state estimation. Now let's move one step beyond the standard Kalman filter. Because in reality, most robotic systems are nonlinear. Robots rotate, they move in curves. Sensor measures angles or ranges. All of this introduces nonlinear behavior. And this is where the extended Kalman filter comes in. The extended Kalman filter is essentially an extension of Kalman filter designed to handle nonlinear systems. It uses something called a first-order Taylor expansion to locally linearize the nonlinear system. It approximates the nonlinear system as linear, but only around the current estimate. So at every step, the extended Kalman filter predicts using the nonlinear motion model, linearizes the model around the current estimate, and updates using the measurement. This allows it to apply the Kalman framework to real-world robotic systems. Because of this, the extended Kalman filter is widely used in mobile robot localization, UAV navigation, visual inertial odometry, or SLAM systems. If you have worked with RAS-based localization stacks or drone navigation, chances are you have encountered an extended Kalman filter. However, it's important to understand its limitation. Since the extended Kalman filter relies on local linear approximation, it can diverge if the system is highly nonlinear or if the initial estimate is poor. In other words, if the approximation becomes inaccurate, the filter can become unstable. Still, despite this limitation, the extended Kalman filter remains one of the most widely used state estimation methods in robotics. It's practical, efficient, and powerful, especially when the system behaves reasonably well around its operating point. Now let's talk about a more advanced alternative to the extended Kalman filter, the unscented Kalman filter, or UKF. Remember how the extended Kalman filter handles nonlinear systems. It linearizes them using a first-order Taylor expansion. The UKF takes a different approach. Instead of approximating the nonlinear function, it approximates the probability distribution itself, and it does this using something called sigma points. Rather than forcing the nonlinear system to behave linearly, the UKF selects a set of carefully chosen sample points, the sigma points, around the current estimate. These points are then passed through the full nonlinear equations. After that, the filter reconstructs the new mean and covariance from the transform points. So instead of linearizing the model, the UKF captures how uncertainty actually flows through the nonlinear system. Because of this, the UKF performs better in highly nonlinear systems. It typically provides higher estimation accuracy than the extended Kalman filter, better handling of nonlinear transformations, or more reliable covariance propagation. However, there is a trade-off. The UKF is more computationally intensive. It requires propagating multiple sigma points at every step, which increases processing cost. So in practice, the choice between extended Kalman filter or UKF depends on your system. If nonlinearities are mild or computation is limited, extended Kalman filter may be sufficient. But if the system is strongly nonlinear and accuracy is critical, the UKF is often the better choice. Now let's talk about a much simpler approach to sensor fusion, the complementary filter. Unlike Kalman-based methods, this is not built on heavy probabilistic math. Instead, it works in the frequency domain. Here is the core idea. Different sensors are good at different frequency ranges. Some sensors are reliable in the short term, others are reliable in the long term. The complementary filter simply blends them based on that strength. A classic example is IMU orientation estimation. A gyroscope measures angular velocity. It's excellent at capturing fast, high-frequency motion, but over time it drifts. An accelerometer, on the other hand, gives a gravity reference. It's stable in the long term, but it's noisy during fast movement. So what do? We trust the gyroscope for rapid changes, and we trust the accelerometer for slow long-term correction. High frequency from gyro, low frequency from accelerometer. An accelerometer, on the other hand, gives a gravity reference. It's stable in the long term, but it's noisy during fast movements. So what do? We trust the gyroscope for rapid changes, and we trust the accelerometer for a slow rapid term correction. High frequency from gyro and low frequency from the accelerometer. They complement each other. The result is a stable orientation estimation without heavy computation. Because of its simplicity, the complementary filter is lightweight, easy to implement. It may not be mathematically powerful as a Kalman filter, but for many real-world applications, especially in resource-constrained systems, it works remarkably well. Today we build the core idea behind sensor fusion. A robot doesn't know its state, it estimates it. It predicts using motion model, corrects using sensor measurements, and manages uncertainty through probability. That simple recursive loop, predict and correct, is the foundation of autonomous systems. Kalman filters, extended Kalman filter, UKF, and particle filters are all built on that same principle. If this helped clarify the fundamentals, support TechLab and comment what we should cover next. In the next episode, we will explore the different types and architectures of sensor fusion in more detail. I will see you there.